Question 1. Risk assessment procedures indicate that integrating data from a third-party financial services API into a Google Cloud data warehouse presents potential risks related to data integrity, security, and compliance with financial data regulations. Which of the following approaches best mitigates these risks? Option A. Directly ingest the raw API response into a Google Cloud storage bucket without any validation or transformation, assuming the API provider guarantees data accuracy and security. Option B. Implement a robust data validation pipeline that enforces schema adherence, encrypts data both in transit using TLS and at rest using Google Cloud's encryption, and establishes comprehensive monitoring with alerts for anomalies and API errors, while strictly adhering to the API's terms of service and rate limits. Option C. Process the API data in real time without any intermediate storage or validation, pushing it directly into the data warehouse to minimize latency, regardless of potential data quality issues or security concerns. Option D. Rely solely on the API provider's authentication mechanism and assume that all data transmitted is inherently secure and compliant with all relevant financial regulations. Correct answer is B. Implement a robust data validation pipeline that enforces schema adherence, encrypts data both in transit using TLS and at rest using Google Cloud's encryption, and establishes comprehensive monitoring with alerts for anomalies and API errors, while strictly adhering to the API's terms of service and rate limits. Explanation. Scenario analysis. This scenario presents a common challenge in data engineering, integrating data from disparate external APIs while ensuring compliance with data privacy regulations and maintaining data integrity. The challenge lies in balancing the need for timely and comprehensive data with the inherent risks associated with external data sources, such as inconsistent formats, potential security vulnerabilities, and varying data quality. A professional data engineer must navigate these complexities to build a robust and compliant data integration pipeline. Correct approach analysis. The correct approach involves implementing a multi-layered strategy that prioritizes data validation, security, and adherence to the API provider's terms of service and relevant data protection laws. This includes establishing clear data contracts, performing rigorous schema validation, encrypting data in transit and at rest, and implementing robust error handling and monitoring. This approach represents best professional practice because it directly addresses the identified risks. Regulatory compliance, particularly concerning data privacy, e.g., GDPR if applicable to the exam's jurisdiction, though for this exam, we assume a US-centric framework like CCPA or HIPAA if health data is involved, or general data security best practices, is paramount. By validating data against expected schemas, the engineer ensures data quality and reduces the risk of downstream processing errors. Encryption protects sensitive data from unauthorized access, a critical security and ethical imperative. Implementing comprehensive monitoring and alerting allows for prompt detection and remediation of issues, minimizing data loss or corruption and maintaining service availability. This proactive and layered security posture is essential for building trust and ensuring the reliability of the data platform. Incorrect approaches analysis. One incorrect approach would be to directly ingest data from the API into a data lake without any intermediate validation or transformation. This fails to address the risk of malformed or erroneous data, which could corrupt the data lake and lead to inaccurate insights. Ethically and regulatorily, this could result in the processing of inaccurate personal data, potentially violating data privacy principles, and leading to compliance issues if sensitive information is involved. Another incorrect approach would be to rely solely on the API provider's security measures without implementing any encryption or access controls on the data once it's ingested into Google Cloud. This creates a significant security vulnerability, exposing data to potential breaches. This is a direct failure to uphold data security best practices and could lead to severe regulatory penalties and loss of trust if sensitive data is compromised. A third incorrect approach would be to ignore the API's rate limits and quotas, leading to frequent service disruptions and potential blacklisting by the API provider. This not only impacts the reliability of the data integration, but also demonstrates a lack of professional diligence in understanding and respecting external service constraints. This can lead to operational failures and, in a business context, financial losses due to unavailable data. Professional reasoning. Professionals should approach data integration from external APIs with a risk-based mindset. This involves a thorough understanding of the data source, its potential vulnerabilities, and the regulatory landscape governing the data. The process should begin with a detailed assessment of the API's documentation, including its data formats, security protocols, and usage policies. Subsequently, a robust architecture should be designed that incorporates layers of defense, secure connection methods, data validation and sanitization, encryption, access control, and continuous monitoring. Establishing clear data governance policies and ensuring that all integrations align with these policies and relevant regulations is crucial. When faced with uncertainty, consulting with security and legal experts is a sign of professional maturity and responsibility. Question 2. Examination of the data shows a diverse set of sources including a live MySQL database with transactional data, a MongoDB cluster storing user profiles, a Kafka topic publishing real-time sensor readings, a daily batch of CSV files containing sales reports, and an external REST API providing market data. The goal is to ingest this data into Google Cloud for analytical processing and reporting. Option A. Utilize only cloud storage for all data ingestion, converting all data to a proprietary binary format before uploading, and then processing it with a custom-built distributed system on GKE. Option B. Manually download all CSV files daily, upload them to a GCS bucket, and then use a single, large data flow job to process all data from all sources, including polling the API and querying the databases directly. Option C. Load all data, regardless of source type or latency, into a single, large PostgreSQL instance on Compute Engine, and then export it to BigQuery. Option D. Ingest MySQL data using Cloud SQL replication or data stream, MongoDB data using a custom connector with Dataflow, Kafka data via pub/sub and Dataflow, CSV files into cloud storage and processed by Dataproc, and API data fetched by Cloud Functions and stored in cloud storage before BigQuery ingestion. The correct answer is D. Ingest MySQL data using Cloud SQL replication or data stream, MongoDB data using a custom connector with Dataflow, Kafka data via pub/sub and Dataflow, CSV files into cloud storage and processed by Dataproc, and API data fetched by Cloud Functions and stored in cloud storage before BigQuery ingestion. Explanation. This scenario presents a common challenge in data engineering, integrating diverse data sources with varying characteristics and latency requirements into a unified analytical platform on Google Cloud. The professional challenge lies in selecting the most appropriate Google Cloud services and architectural patterns to efficiently and cost-effectively ingest, process, and store data from relational databases, NoSQL stores, streaming sources, flat files, and APIs, while adhering to potential data governance and compliance requirements relevant to the Google Cloud Professional Data Engineer exams assume jurisdiction, which for this exam is U.S.-centric, focusing on general best practices and common U.S. regulatory principles like data privacy and security, without specific statute citations, unless explicitly provided. The correct approach involves a multifaceted strategy that leverages Google Cloud's managed services tailored to the specific needs of each data source. For relational and NoSQL databases, services like Cloud SQL or DataStream for continuous replication or Dataflow for batch ETL are suitable. Streaming data from Kafka or pub/sub is best handled by pub/sub for ingestion and Dataflow for real-time processing. Files like CSV, JSON, and Parquet are efficiently managed by cloud storage, with Dataflow or Dataproc for processing. APIs can be integrated using Cloud Functions or Cloud Run to fetch data, which can then be landed in cloud storage or directly ingested into BigQuery. This approach represents best professional practice because it prioritizes scalability, reliability, cost efficiency, and maintainability by using managed services that abstract away infrastructure management. It allows for flexible data pipelines that can adapt to changing data volumes and velocities. Incorrect approaches would involve misapplying services or architectural patterns, leading to inefficiencies, increased costs, or security vulnerabilities. For instance, attempting to stream all data through a single, monolithic batch process would fail to meet the latency requirements of real-time sources and would be overly complex and expensive. Similarly, Using only manual file transfers for all data types would be unscalable and prone to errors, neglecting the benefits of automated ingestion. Relying solely on a single database technology for all data, regardless of its structure or access pattern, would be inefficient and costly. Each incorrect approach represents a failure to understand the strengths and weaknesses of different data sources and Google Cloud services, potentially leading to data silos, performance bottlenecks, and increased operational overhead. From a U.S. regulatory perspective, a failure to properly secure data from various sources or to implement appropriate access controls could lead to breaches of privacy regulations like HIPAA, if health data is involved, or CCPA, resulting in significant fines and reputational damage. The professional decision-making process should involve a thorough assessment of each data source's characteristics: volume, velocity, variety, veracity, and value. This assessment should then be mapped against the capabilities of available Google Cloud services. Key considerations include latency requirements, data transformation needs, security and compliance mandates, cost constraints, and the team's existing skill set. A phased approach, starting with the most critical data sources and iteratively building out the data platform, is often advisable. Question 3. Performance analysis shows that a regression model predicting user engagement with a new feature has a high R-squared value and statistically significant coefficients for several user attributes. The product team wants to roll out the feature to all users based on these findings. What is the most appropriate next step to validate these findings and ensure responsible deployment? Option A. Focus on refining the regression model by adding more complex interaction terms to further increase its predictive accuracy. Option B. Conduct an A/B test to compare user engagement with the new feature against a control group without the feature. Option C. Perform a time series analysis on historical engagement data to identify any seasonal trends that might influence the regression results. Option D. Immediately deploy the feature to all users, as the regression model's statistical significance indicates a strong positive impact. Correct answer is B. Conduct an A/B test to compare user engagement with the new feature against a control group without the feature. Explanation. This scenario presents a common challenge in data engineering, interpreting the results of a statistical model to inform business decisions, while adhering to regulatory and ethical standards. The challenge lies in distinguishing between a statistically significant finding and a practically meaningful one, and ensuring that the chosen approach is robust, interpretable, and compliant with data privacy and fairness principles. The correct approach involves a rigorous statistical validation process that considers not only the model's predictive power, but also its interpretability and potential biases. This aligns with best professional practices by ensuring that decisions are data-driven, transparent, and ethically sound. Specifically, when dealing with user-facing features or product changes, A/B testing is a critical regulatory and ethical safeguard. It allows for controlled experimentation, minimizing the risk of negative impacts on a broad user base and providing clear, quantifiable evidence of a change's effect. This methodical approach ensures that any proposed changes are validated before full deployment, thereby mitigating risks of user dissatisfaction, reputational damage, and potential regulatory scrutiny related to unfair or discriminatory practices if the model were to inadvertently impact certain user segments negatively. Incorrect approaches fail to adequately address the inherent risks and regulatory considerations. For instance, relying solely on a regression model without A/B testing to justify a product change overlooks the potential for confounding variables and the real-world impact on user behavior. This could lead to a situation where a statistically significant correlation is misinterpreted as causation, resulting in a detrimental product change. From a regulatory perspective, deploying a change based on such incomplete evidence could violate principles of consumer protection and fair practice, especially if the change disproportionately affects certain user groups. Another incorrect approach might involve overinterpreting a single metric from a complex model without understanding its limitations or potential biases. This can lead to flawed decision-making and, in regulated industries, could result in non-compliance with data governance and auditability requirements. Ethical failures include a lack of due diligence in validating the impact of changes on users and a disregard for the principles of responsible AI and data usage. The professional decision-making process should involve a multi-stage validation strategy. First, exploratory data analysis and initial model building, like regression, to identify potential drivers. Second, rigorous hypothesis testing to confirm the statistical significance of observed effects. Third, and crucially for user-facing changes, a/B testing to measure the real-world impact and validate the model's predictions in a controlled environment. Finally, a thorough review of the results, considering both statistical significance and practical implications, alongside ethical and regulatory compliance, before making a final decision. This iterative and cautious approach ensures that data-driven insights are translated into responsible and effective actions. Question 4. The monitoring system demonstrates a gradual but consistent decline in the accuracy of a deployed machine learning model used for customer churn prediction. The data pipeline appears to be functioning correctly, and there are no immediate indications of data quality issues. The team needs to decide on the next steps to address this performance degradation. Option A. Implement a random forest model as a replacement, leveraging its ensemble nature to potentially capture more nuanced patterns in the data. Option B. Reevaluate the model choice, considering simpler, more interpretable models like decision trees or linear regression, to better diagnose the root cause of the performance drop. Option C. Immediately retrain the existing model with the latest data, assuming the drift is a natural consequence of evolving customer behavior. Option D. Replace the current model with a more complex neural network architecture, expecting that increased model capacity will inherently improve performance. The correct answer is B. Reevaluate the model choice, considering simpler, more interpretable models like decision trees or linear regression, to better diagnose the root cause of the performance drop. Explanation. Scenario analysis. This scenario presents a common challenge in machine learning operations: model drift and the need for continuous evaluation and potential retraining. The challenge lies in identifying the root cause of performance degradation and selecting the most appropriate response, balancing accuracy, cost, and regulatory compliance. The professional must not only understand the technical implications of model performance, but also the potential business and ethical ramifications of deploying a suboptimal model. Correct approach analysis. Selecting a model that is inherently more interpretable and less prone to overfitting on noisy data, like a decision tree or a linear model, is best professional practice when dealing with subtle performance degradation. These models allow for easier debugging and understanding of feature importance, which is crucial for identifying the cause of the drift. For instance, if the data distribution has shifted, a decision tree's rules can often highlight which features are contributing to the misclassifications. This aligns with principles of responsible AI, ensuring transparency and accountability in model behavior, which is increasingly important under data governance frameworks that emphasize explainability and fairness. Incorrect approaches analysis. Choosing a complex, black box model like a deep neural network without a clear understanding of the drift's cause is professionally risky. While neural networks can achieve high accuracy, their complexity makes it difficult to diagnose performance issues, potentially leading to prolonged periods of suboptimal performance and increased operational costs. This lack of transparency can also be problematic from a regulatory perspective if the model's decisions are subject to scrutiny, as it hinders the ability to explain why a particular outcome occurred. Opting for a random forest without further investigation is also suboptimal. Random forests are robust and can handle complex relationships. They are an ensemble of decision trees and can inherit some of the interpretability challenges of their base learners, especially when dealing with a large number of trees. Diagnosing drift in a random forest can be more complex than in a single decision tree, requiring more sophisticated feature importance analysis. Selecting an SVM without considering the nature of the data and the observed drift is also not ideal. SVMs can be powerful, but their decision boundaries can become complex, and understanding the reasons for performance degradation can be challenging, especially with nonlinear kernels. This can lead to a reactive rather than proactive approach to model maintenance. Professional reasoning. Professionals should employ a structured decision-making framework. First, thoroughly investigate the observed performance degradation. This involves analyzing prediction errors, feature drift, and data quality issues. Second, consider the trade-offs between model complexity, interpretability, and performance. For this scenario, prioritizing interpretability to diagnose the root cause is paramount. Third, Evaluate the cost and feasibility of retraining or replacing the model. Finally, ensure that the chosen approach aligns with any relevant data governance policies or ethical guidelines, emphasizing transparency and fairness. Question 5. Analysis of a scenario where a data engineering team is tasked with building a new data pipeline to ingest, transform, and load customer interaction data from various sources into a data warehouse. The pipeline needs to handle both batch and streaming data, be highly scalable, and require robust monitoring and alerting to ensure data quality and availability. The team is considering different approaches to orchestrate and manage this pipeline. Which of the following approaches best aligns with professional best practices for building and operating such a data pipeline on Google Cloud Platform? Option A. Develop custom Python scripts for data transformation and use cron jobs for scheduling, with basic log file analysis for monitoring. Option B. Focus solely on building the transformation logic in Cloud Dataflow without implementing a dedicated orchestration tool or robust alerting mechanisms, assuming the data volume will remain constant. Option C. Utilize Cloud Dataflow with Apache Beam for processing, Cloud Composer for workflow orchestration and scheduling, and integrate with cloud monitoring and alerting for comprehensive observability. Option D. Manually provision and manage virtual machines for all data processing tasks, orchestrate workflows using shell scripts, and rely on manual checks for monitoring. The correct answer is C. Utilize Cloud Dataflow with Apache Beam for processing, Cloud Composer for workflow orchestration and scheduling, and integrate with cloud monitoring and alerting for comprehensive observability. Explanation. This scenario presents a common challenge for data engineers, balancing the need for robust, scalable data processing with the operational realities of monitoring and alerting in a production environment. The challenge lies in selecting the right combination of tools and configurations to ensure data pipelines are not only functional, but also observable and maintainable, minimizing downtime and data integrity issues. Careful judgment is required to avoid over-engineering or under-provisioning, both of which can lead to significant business impact. The correct approach represents best professional practice because it leverages Cloud Dataflow and Apache Beam for their inherent scalability and portability, while utilizing Cloud Composer for sophisticated workflow orchestration and integrated monitoring. Apache Beam's unified programming model allows for efficient batch and stream processing, and its execution on Cloud Dataflow ensures managed infrastructure and auto-scaling. Cloud Composer, built on Apache Airflow, provides a robust framework for defining, scheduling, and monitoring complex data pipelines, including dependency management and error handling. The integration of cloud monitoring and alerting ensures proactive identification of issues, enabling rapid response and minimizing data loss or corruption. This combination adheres to best practices for reliability, maintainability, and operational efficiency, crucial for any professional data engineering role. An incorrect approach that relies solely on manual scripting for orchestration and basic cron jobs for scheduling would fail ethically and professionally by neglecting industry-standard practices for robust workflow management. This approach is prone to errors, difficult to scale, and lacks comprehensive monitoring capabilities, increasing the risk of undetected pipeline failures and data inconsistencies. From a regulatory perspective, while not directly violating specific laws in this context, it demonstrates a failure to implement due diligence in data pipeline management, which could have downstream implications for data governance and compliance if data integrity is compromised. Another incorrect approach that focuses heavily on custom, low-level infrastructure management without leveraging managed services like Cloud Dataflow or Cloud Composer would be professionally unsound. This would lead to increased operational overhead, higher potential for misconfiguration, and a lack of standardized monitoring and alerting. Ethically, it represents a failure to utilize available, more reliable tools, potentially exposing the organization to unnecessary risks. A third incorrect approach that prioritizes speed of development over robust monitoring and alerting would be professionally negligent. A rapid deployment is sometimes a business requirement. Neglecting observability in critical data pipelines is a direct path to production issues that can be difficult and time-consuming to diagnose and resolve. This oversight can lead to significant business disruption and a loss of stakeholder trust, representing a failure in professional responsibility. The professional decision-making process for similar situations should involve a thorough assessment of business requirements, data volume and velocity, complexity of transformations, and the need for real-time processing. It should then involve evaluating available tools against these requirements, prioritizing managed services for scalability and reliability, and ensuring comprehensive monitoring and alerting are integrated from the outset. A phased approach, starting with a core set of functionalities and iteratively adding complexity and monitoring, is often advisable. Question 6. The evaluation methodology shows that a financial services company is migrating sensitive customer data to Google Cloud. The company must ensure data is protected at rest and in transit, that access is strictly controlled, and that personally identifiable information, PI, is appropriately handled to comply with data privacy regulations. Which combination of Google Cloud services and configurations best addresses these requirements? Option A. Use Google Cloud's default server-side encryption for data at rest. Grant read access to the entire dataset to all employees, and do not implement any data anonymization, as encryption is considered sufficient. Option B. Enable server-side encryption for data at rest, but not for data in transit. Grant administrative access to the entire data lake to all data engineers, and only anonymize data when explicitly requested by a customer. Option C. Rely solely on client-side encryption for all data before uploading it to Google Cloud. Grant broad read access to the data analytics team, and store all PII in its raw form for maximum analytical flexibility. Option D. Enable Google Cloud's default server-side encryption for data at rest and in transit. Implement fine-grained IAM roles based on the principle of least privilege for all data access, and utilize data masking and anonymization techniques for PII in non-production environments, and for analytical workloads where direct PII is not required. The correct answer is D. Enable Google Cloud's default server-side encryption for data at rest and in transit. Implement fine-grained IAM roles based on the principle of least privilege for all data access, and utilize data masking and anonymization techniques for PII in non-production environments, and for analytical workloads where direct PII is not required. Explanation. This scenario presents a common challenge in cloud data engineering, balancing robust data security with operational efficiency and compliance. The professional must navigate the complexities of Google Cloud security features and understand how they align with regulatory requirements for data protection, specifically focusing on encryption, access control, and anonymization. The challenge lies in selecting the most appropriate combination of tools and configurations to meet these demands without compromising data usability or introducing unnecessary risks. The correct approach represents best professional practice because it leverages Google Cloud's native encryption capabilities for data at rest and in transit, ensuring that sensitive information is protected by default. It also implements a granular IAM strategy, adhering to the principle of least privilege, which is a cornerstone of effective access control and a key regulatory expectation. Furthermore, it employs data anonymization techniques where appropriate, reducing the risk of re-identification and complying with privacy regulations that mandate minimizing the exposure of personal data. This comprehensive strategy directly addresses the core tenets of data security and privacy mandated by regulatory frameworks. An incorrect approach that relies solely on client-side encryption without server-side encryption fails to protect data once it is at rest on Google Cloud infrastructure, creating a significant security gap. This is a regulatory failure as it does not provide adequate protection for data stored in the cloud. Another incorrect approach that grants broad access permissions to a large group of users, even with the intention of simplifying operations, violates the principle of least privilege. This is a critical access control failure and a direct contravention of regulatory requirements for data protection, increasing the risk of unauthorized access and data breaches. An approach that neglects data anonymization for sensitive datasets, even if encrypted, exposes individuals to potential re-identification risks if encryption is compromised or if metadata is not properly handled. This represents a failure to adequately protect personal data as required by privacy regulations. Professionals should approach such decisions by first identifying the specific data sensitivity levels and regulatory obligations applicable to the data being processed. They should then map these requirements to the available security features within Google Cloud, prioritizing native services that offer integrated security and compliance. A layered security approach, combining encryption, robust access controls, and appropriate data transformation techniques like anonymization, is essential. Regular security audits and adherence to established security best practices, such as the principle of least privilege, are crucial for maintaining a secure and compliant data environment. Question 7. The assessment process reveals that a critical customer analytics dataset, sourced from multiple disparate systems, exhibits significant inconsistencies in customer address formats, a high percentage of missing demographic information, and varying data types for purchase dates. To optimize the data pipeline for downstream reporting and machine learning, which of the following strategies best addresses these data quality issues while ensuring process efficiency and data integrity? Option A. Implement an automated data quality framework that defines standardized address formats, employs intelligent imputation techniques for missing demographic data based on statistical analysis, and enforces consistent date formats through data type coercion and validation rules. Option B. Discard all records containing any missing demographic information and apply a simple string manipulation to standardize addresses without considering regional variations or date parsing logic. Option C. Manually review and correct all address entries, remove any customer records with incomplete demographic information, and convert all purchase dates to a single, arbitrary string format. Option D. Rely on the downstream reporting tools to handle address formatting inconsistencies, impute missing demographic data using a default placeholder value for all records, and ignore purchase date data type discrepancies. Correct answer is A. Implement an automated data quality framework that defines standardized address formats, employs intelligent imputation techniques for missing demographic data based on statistical analysis, and enforces consistent date formats through data type coercion and validation rules. Explanation. The assessment process reveals a common challenge in data engineering, ensuring data quality and consistency across diverse sources before it's used for critical business decisions or machine learning model training. This scenario is professionally challenging because the consequences of poor data quality can range from inaccurate insights and flawed predictions to significant financial losses and reputational damage. The sheer volume and variety of data, coupled with evolving business requirements, necessitate a robust and adaptable data validation and cleansing strategy. Careful judgment is required to balance the need for thoroughness with the imperative of timely data delivery. The correct approach represents best professional practice because it prioritizes a systematic and automated process for data validation and cleansing. This involves defining clear data quality rules, implementing automated checks for anomalies and inconsistencies, and employing appropriate techniques for handling missing values and standardizing data formats. Such an approach ensures that data is reliable, consistent, and fit for purpose, thereby supporting accurate analysis and informed decision-making. This aligns with the ethical obligation to provide trustworthy data and the professional responsibility to maintain high standards of data integrity. An incorrect approach that relies solely on manual inspection and ad hoc corrections is professionally unacceptable. This method is prone to human error, is not scalable, and fails to establish repeatable processes. It can lead to inconsistent data quality over time and makes it difficult to audit or reproduce the cleansing steps. Ethically, it risks propagating errors and misleading stakeholders. Another incorrect approach that involves discarding all records with missing values without proper analysis is also professionally flawed. While seemingly simple, this can lead to significant data loss, potentially biasing the dataset and skewing analytical results. It fails to consider the potential value of incomplete records or the possibility of imputing missing values intelligently. This can violate the principle of using data responsibly and comprehensively. A third incorrect approach that applies transformations without understanding their impact on data distribution or downstream analysis is also problematic. Unintended consequences of transformations can render data unsuitable for its intended use. This demonstrates a lack of due diligence and can lead to inaccurate conclusions, failing to uphold the professional standard of ensuring data utility and integrity. The professional reasoning process for similar situations should involve 1. Understanding the data sources and their inherent quality issues. 2. Defining clear data quality metrics and validation rules aligned with business objectives. 3. Designing an automated pipeline for data validation and cleansing, incorporating error logging and alerting. 4. Selecting appropriate methods for handling missing values, e.g., imputation, deletion with justification, based on data characteristics and analytical goals. 5. Implementing data standardization techniques to ensure consistency in formats, units, and representations. 6. Regularly monitoring data quality and iterating on the cleansing process as needed. 7. Documenting all validation and cleansing steps for transparency and reproducibility. Question 8. Research into a customer churn prediction model deployed on Google Cloud has revealed that while the model achieves high overall accuracy, it exhibits a statistically significant tendency to incorrectly predict churn for customers belonging to a specific demographic group. The data engineering team needs to address this fairness issue without compromising the model's predictive power or violating data privacy regulations. Which approach best addresses this challenge? Option A. Utilize Vertex AI fairness tools to analyze the bias, identify contributing factors, and apply appropriate mitigation techniques to improve fairness metrics while monitoring accuracy. Option B. Increase the complexity of the model by adding more features and hyperparameter tuning, assuming this will implicitly resolve any fairness issues. Option C. Focus solely on optimizing the model for the highest possible overall accuracy, as this is the primary business objective. Option D. Remove the sensitive demographic attribute from the training data, believing this will eliminate any bias related to that group. The correct answer is A. Utilize Vertex AI fairness tools to analyze the bias, identify contributing factors, and apply appropriate mitigation techniques to improve fairness metrics while monitoring accuracy. Explanation. This scenario presents a common challenge in machine learning projects, balancing the need for robust model performance with the ethical imperative of fairness and the regulatory requirement for transparency and accountability. The professional challenge lies in identifying and mitigating bias in a way that is both technically sound and compliant with data privacy and non-discrimination principles, which are implicitly governed by general data protection and ethical AI guidelines relevant to the U.S. context for this exam. Careful judgment is required to ensure that the chosen approach not only improves model accuracy, but also upholds ethical standards and avoids potential legal repercussions. The correct approach represents best professional practice because it directly addresses the identified bias through a systematic and verifiable method. By leveraging Google Cloud's Vertex AI fairness tools, the data engineer can quantify bias, understand its sources, and implement targeted mitigation strategies. This aligns with the principles of responsible AI development, emphasizing transparency in identifying and addressing fairness issues. Furthermore, using documented tools and processes ensures auditability, which is crucial for regulatory compliance and demonstrating due diligence in preventing discriminatory outcomes. This proactive and data-driven approach to bias mitigation is essential for building trust and ensuring equitable outcomes for all users. An incorrect approach that relies solely on increasing model complexity without explicitly addressing bias is professionally unacceptable. This is because it risks exacerbating existing biases or introducing new ones, leading to discriminatory outcomes. Ethically, this fails to uphold the principle of fairness and could result in disparate impact on protected groups. From a regulatory perspective, it demonstrates a lack of due diligence in ensuring the model's outputs are equitable and non-discriminatory, potentially violating anti-discrimination laws. Another incorrect approach that involves removing sensitive attributes without a thorough understanding of their correlation with other features is also professionally unacceptable. While seemingly a straightforward solution, removing sensitive attributes can lead to proxy discrimination if other features indirectly capture the same discriminatory information. This approach lacks the analytical rigor required to ensure true fairness and can mask underlying biases rather than resolve them, leading to ethical and regulatory failures related to unintended discrimination. Finally, an approach that prioritizes only overall accuracy metrics without considering fairness metrics is professionally deficient. Focusing solely on accuracy can lead to a model that performs well on average, but exhibits significant performance disparities across different demographic groups. This overlooks the ethical obligation to ensure equitable treatment and can result in regulatory noncompliance if the model's inaccuracies disproportionately harm certain groups. The professional reasoning process for similar situations should involve a multi-step approach. First, clearly define the problem and the desired outcomes, including fairness objectives. Second, leverage appropriate tools and techniques to assess model performance and identify potential biases. Third, explore and implement bias mitigation strategies, carefully evaluating their impact on both accuracy and fairness. Fourth, document all steps taken, including the rationale for chosen approaches and the results of evaluations. Finally, continuously monitor the model in production for any emergent biases or performance degradation, ensuring ongoing adherence to ethical and regulatory standards. Question 9. Governance review demonstrates that the current data lake design on Google Cloud Storage is experiencing escalating costs and inconsistent query performance. The data lake stores a variety of datasets, including real-time streaming data, historical analytical data, and archival logs. The team needs to optimize storage costs and improve query efficiency without compromising data availability for different access frequencies. Which of the following approaches best addresses these challenges? Option A. Migrate all data to Google Cloud Storage Nearline to achieve a balance between cost and retrieval time, and implement a simple prefix-based partitioning strategy for all datasets to organize them logically. Option B. Utilize Google Cloud Storage Archive class for all historical and archival data to minimize storage costs, and implement a complex, highly granular partitioning scheme based on individual record attributes to facilitate very specific data retrieval. Option C. Implement a tiered storage strategy using Google Cloud Storage classes, standard, nearline, coldline archive, with lifecycle management rules to automatically transition data based on age and access frequency. Concurrently, adopt a partitioning strategy for frequently accessed analytical data based on date, year/month/day, and for less frequently accessed data based on broader timeframes or other relevant dimensions to optimize query performance and reduce scan costs. Option D. Consolidate all data into Google Cloud Storage Standard class to ensure maximum availability and performance for all datasets, and rely on manual data management for any cost optimization efforts. The correct answer is C. Implement a tiered storage strategy using Google Cloud Storage classes, standard, nearline, coldline archive, with lifecycle management rules to automatically transition data based on age and access frequency. Concurrently, adopt a partitioning strategy for frequently accessed analytical data based on date, year/month/day, and for less frequently accessed data based on broader timeframes or other relevant dimensions to optimize query performance and reduce scan costs. Explanation. This scenario presents a common challenge in cloud data engineering: balancing cost efficiency, performance, and data accessibility in a large-scale object storage environment. The core difficulty lies in designing a data lake strategy that accommodates diverse data types and access patterns, while adhering to potential regulatory requirements for data retention and access control, all within the constraints of a specific cloud provider's services. The need to optimize for both frequent and infrequent access, as well as the potential for data growth, requires a nuanced approach to object storage and partitioning. The correct approach represents best professional practice because it leverages Google Cloud Storage tiered storage classes and intelligent lifecycle management to automatically move data to more cost-effective storage as it ages, while also implementing a logical partitioning strategy based on common query patterns. This ensures that frequently accessed data remains performant, infrequently accessed data is stored economically, and query efficiency is maintained through effective data organization. This aligns with principles of responsible data management, aiming for optimal resource utilization and cost control, which are implicit in professional data engineering standards. An incorrect approach that focuses solely on a single storage class without considering access patterns would lead to either overspending on frequently accessed data that could be archived or performance degradation for critical data if it's all placed in a low-cost, high-latency tier. This failure to optimize resource allocation is professionally unsound. Another incorrect approach that ignores partitioning or uses an inefficient partitioning scheme would result in poor query performance, increased costs due to full bucket scans, and potential difficulties in managing data access and retention at a granular level. This lack of foresight in data organization directly impacts operational efficiency and can lead to compliance issues if data cannot be effectively managed or purged as required by regulations. A third incorrect approach that prioritizes only raw storage cost without considering access patterns or data lifecycle would lead to significant long-term cost inefficiencies and potential performance bottlenecks, demonstrating a lack of strategic planning. Professionals should approach such situations by first understanding the data's characteristics, access patterns, and any relevant regulatory or business requirements. This involves analyzing query logs, understanding data freshness needs, and identifying data lifecycle policies. Then, they should evaluate the cloud provider's services, such as storage tiers and lifecycle management features, and design a partitioning strategy that aligns with anticipated query patterns and data management needs. Iterative testing and monitoring are crucial to validate the chosen strategy and make adjustments as data usage evolves. Question 10. Strategic planning requires a robust and scalable data warehousing solution on Google Cloud to support an e-commerce platform experiencing rapid growth. The platform needs to cater to both real-time operational reporting and complex analytical queries for business intelligence. Data security and granular access control are paramount due to the presence of sensitive customer information. Which of the following approaches best addresses these requirements while adhering to Google Cloud best practices for BigQuery? Option A. Design a star schema for analytical workloads, implement date-based partitioning and column-based clustering in BigQuery tables, and manage data loading and transformations using SQL and Dataflow, with access control enforced via BigQuery IAM policies. Option B. Implement a snowflake schema to maximize data normalization and minimize redundancy, loading data in batches and relying on client-side applications for all data transformations, with broad access granted to all internal users. Option C. Create a single, denormalized table for all data, without any partitioning or clustering, and use manual CSV uploads for data loading, with no specific access controls configured beyond project-level permissions. Option D. Utilize a star schema but load all data through complex UDFs written in Python for all transformations, and implement access control solely through network firewalls. The correct answer is A. Design a star schema for analytical workloads, implement date-based partitioning and column-based clustering in BigQuery tables, and manage data loading and transformations using SQL and Dataflow, with access control enforced via BigQuery IAM policies. Explanation. Scenario analysis. This scenario presents a common challenge in data engineering, where a rapidly growing e-commerce platform needs to scale its data warehousing capabilities on Google Cloud. The core challenge lies in balancing performance, cost, and maintainability while adhering to data governance and security best practices. The need to support both analytical queries for business intelligence and operational reporting introduces complexity in schema design and data loading strategies. The strict requirement for data security and access control, especially with sensitive customer data, necessitates a robust and compliant approach. Correct approach analysis. Implementing a star schema with appropriate partitioning and clustering in BigQuery represents best professional practice. A star schema is optimized for analytical queries, reducing join complexity and improving performance, which is crucial for BI and reporting. Partitioning by date, e.g., ingestion date or transaction date, significantly reduces query scan costs and improves performance by allowing BigQuery to scan only relevant partitions. Clustering by frequently filtered or joined columns, e.g., customer ID, product ID, further optimizes query performance by co-locating related data within partitions. Data loading should leverage BigQuery's native streaming or batch loading capabilities, with transformations handled efficiently using SQL or serverless options like Dataflow for complex ETL/ELT. Access control should be implemented using BigQuery's IAM policies at the dataset and table levels, ensuring least privilege access for different user roles, e.g., analysts, data scientists, operational teams. This approach aligns with Google Cloud's recommended practices for BigQuery performance and cost management, and with general data governance principles of data security and efficient access. Incorrect approach is analysis. Choosing a snowflake schema without careful consideration would be a regulatory/ethical failure. while a snowflake schema offers normalization and reduces data redundancy. It often leads to more complex queries with numerous joins, negatively impacting performance and increasing query costs in BigQuery. This inefficiency could lead to missed business insights due to slow reporting or increased operational expenses, potentially violating cost management principles. Implementing a single, massive table without partitioning or clustering would be a significant regulatory/ethical failure. This approach would lead to extremely slow query performance and prohibitively high scan costs, as BigQuery would have to scan the entire table for every query. This directly contravenes the principle of efficient resource utilization and could lead to non-compliance with cost optimization mandates or service-level agreements for reporting. It also poses a security risk, as it makes granular access control more challenging. Relying solely on client-side transformations for all data loading and transformation would be a regulatory/ethical failure. This approach is inefficient, difficult to scale, and bypasses BigQuery's optimized processing capabilities. It can lead to increased latency, higher costs due to data egress and ingress, and potential data integrity issues if not managed meticulously. Furthermore, it complicates auditing and governance, as transformations are not centralized and managed within the data warehouse environment, potentially violating data lineage and auditability requirements. Professional reasoning. Professionals should approach this scenario by first understanding the analytical and operational requirements. Then, they should evaluate schema design options, prioritizing performance and cost efficiency for BigQuery. Partitioning and clustering are essential for optimizing BigQuery performance and cost. Data loading and transformation strategies should leverage BigQuery's native capabilities or serverless services for scalability and efficiency. Finally, a robust access control strategy using IAM is paramount for data security and compliance. The decision-making process should involve a trade-off analysis between complexity, performance, cost, and security, always prioritizing solutions that are scalable, maintainable, and compliant with data governance principles. Question 11. Which approach would be most appropriate for a financial services firm that needs to detect fraudulent transactions in near real time, while also performing daily risk assessments on historical trading data, considering cost-effectiveness and operational complexity? Option A. A batch pipeline architecture that processes only historical trading data daily for risk assessments, with a separate ad hoc process for fraud detection. Option B. A batch pipeline architecture that processes all transaction and trading data daily for both fraud detection and risk assessments. Option C. A streaming pipeline architecture that processes all transaction and trading data continuously for both fraud detection and risk assessments. Option D. A hybrid pipeline architecture that uses a streaming pipeline for immediate fraud detection and a batch pipeline for daily risk assessments. The correct answer is D. A hybrid pipeline architecture that uses a streaming pipeline for immediate fraud detection and a batch pipeline for daily risk assessments. Explanation. This scenario presents a common challenge in data engineering, balancing real-time data needs with the cost-effectiveness and complexity of different pipeline architectures. The professional challenge lies in selecting an architecture that meets business requirements for data freshness and availability without incurring unnecessary operational overhead or introducing significant latency that could impact downstream decision-making. Careful judgment is required to align technical capabilities with business objectives and regulatory compliance. The correct approach represents best professional practice because it acknowledges the need for both immediate insights and efficient batch processing. By leveraging a hybrid architecture, it allows for low-latency ingestion and processing of critical, time-sensitive events, stream processing, while simultaneously enabling cost-effective and comprehensive analysis of historical and less time-critical data, batch processing. This dual approach optimizes resource utilization and ensures that different data types are handled according to their specific business value and urgency, aligning with principles of efficient data management and operational excellence. In the context of data governance and compliance, this approach allows for granular control over sensitive data streams while maintaining robust audit trails for batch operations, adhering to best practices for data integrity and security. An incorrect approach that relies solely on batch processing would fail to meet the requirement for near real-time insights, potentially leading to delayed business decisions and missed opportunities. This could have indirect regulatory implications if timely reporting or anomaly detection is mandated. An approach that attempts to process all data in a streaming fashion, even historical or less critical data, would likely be prohibitively expensive and complex to manage, leading to inefficient resource allocation and potential system instability. This inefficiency could indirectly impact compliance efforts by straining resources needed for data quality checks and security monitoring. An approach that uses a batch pipeline for critical, time-sensitive data would introduce unacceptable latency, directly contravening the business need for immediate actionable intelligence, and potentially leading to non-compliance with service-level agreements or regulatory requirements that depend on prompt data availability. Professionals should approach such decisions by first clearly defining the data latency requirements for different use cases. Understanding the business impact of data freshness is paramount. Then, evaluate the technical feasibility, cost implications, and operational complexity of batch, stream, and hybrid architectures. A thorough risk assessment, considering potential data loss, processing errors, and security vulnerabilities for each option, is crucial. Finally, the chosen architecture should be validated against relevant data governance policies and any applicable regulatory mandates to ensure compliance and ethical data handling. Question 12. The review process indicates that a new streaming data source is being integrated into the Google Cloud environment. This source contains customer interaction logs, which may include personally identifiable information, PI. The primary goal is to ingest this data into BigQuery for real-time analytics. What is the most appropriate risk assessment approach to ensure compliance and data integrity during this data collection and ingestion phase? Option A. Rely solely on the data source provider's assurances regarding data quality and security, and assume that all data ingested is compliant and accurate without independent verification. Option B. Prioritize ingestion speed above all else, deferring any risk assessment or validation until after the data has been processed and analyzed by the end users. Option C. Proceed with immediate, high-volume ingestion to capture as much data as possible, and address any data quality or PII concerns retrospectively through post-ingestion data cleansing and anonymization scripts. Option D. Implement automated data quality checks and PII detection mechanisms within the ingestion pipeline, alongside a security review of the data source's access controls and data transmission protocols before full-scale ingestion. The correct answer is D. Implement automated data quality checks and PII detection mechanisms within the ingestion pipeline, alongside a security review of the data source's access controls and data transmission protocols before full-scale ingestion. Explanation. This scenario presents a common challenge in data engineering, balancing the need for timely data ingestion with robust risk assessment to ensure compliance and data integrity. The professional challenge lies in identifying potential data quality issues, security vulnerabilities, and regulatory noncompliance before they impact downstream systems or lead to breaches. Careful judgment is required to prioritize ingestion speed against the thoroughness of risk evaluation, especially when dealing with sensitive data or systems with strict uptime requirements. The correct approach represents best professional practice because it embeds a proactive risk assessment directly into the data collection and ingestion pipeline. By establishing clear data quality checks, security protocols, and compliance validation steps as part of the ingestion process, it minimizes the likelihood of introducing erroneous, compromised, or non-compliant data into the system. This aligns with the principles of data governance and security best practices, ensuring that data is trustworthy and handled appropriately from its source. An incorrect approach that bypasses or inadequately performs risk assessment before ingestion is professionally unacceptable due to several regulatory and ethical failures. Firstly, it risks violating data privacy regulations, e.g., if PII is ingested without proper anonymization or consent mechanisms, by failing to identify and mitigate such risks upfront. Secondly, it can lead to data integrity issues, where inaccurate or corrupted data is used for decision-making, potentially causing financial or reputational damage. Thirdly, it increases the attack surface for security breaches by not verifying the security posture of data sources or the ingestion mechanisms themselves, potentially exposing sensitive information. Professionals should adopt a decision-making framework that prioritizes A. security and compliance by design philosophy. This involves understanding the data's sensitivity, its intended use, and the relevant regulatory landscape before designing the ingestion pipeline. When faced with a new data source or ingestion method, a structured risk assessment should be conducted, identifying potential threats and vulnerabilities and defining mitigation strategies. This assessment should then inform the design and implementation of the ingestion process, ensuring that controls are in place to address identified risks. Continuous monitoring and periodic reassessment are also crucial components of this framework. Question 13. The analysis reveals that a retail company intends to use Cloud Vision API to analyze images of its store shelves for inventory management and product placement optimization. The company wants to identify products, detect shelf integrity, and extract product names for cataloging. However, some images may incidentally capture customers in the background. The primary goal is to enhance operational efficiency without compromising customer privacy or violating any data protection regulations. Which of the following configurations for Cloud Vision API best aligns with these objectives and regulatory best practices? Option A. Configure Cloud Vision API to utilize only the object localization and optical character recognition (OCR) features, specifically targeting product identification and shelf text, while explicitly disabling face detection and other personal attribute detection features. Option B. Utilize Cloud Vision API's explicit content detection to flag any potentially inappropriate imagery on shelves or in the background, in addition to product detection. Option C. Enable all Cloud Vision API features, including face detection and landmark detection, and implement a post-processing script to filter out any personally identifiable information. Option D. Enable face detection and attribute analysis to understand customer demographics for better store layout, alongside product detection for inventory. Correct answer is C. Enable all Cloud Vision API features, including face detection and landmark detection, and implement a post-processing script to filter out any personally identifiable information. Explanation. This scenario presents a professional challenge due to the need to balance the powerful capabilities of Cloud Vision API for image analysis with the critical requirement of data privacy and compliance. Organizations must ensure that the insights derived from image data do not inadvertently expose sensitive personal information, especially when dealing with public-facing applications or data that may be subject to regulatory scrutiny. Careful judgment is required to select an implementation strategy that maximizes utility while minimizing risk. The correct approach represents best professional practice because it prioritizes data minimization and anonymization at the source. By configuring Cloud Vision API to detect only specific necessary information, e.g., general objects, text for OCR, and explicitly excluding features that could identify individuals, like face detection, unless explicitly required and consented to, the solution adheres to the principle of least privilege and privacy by design. This proactive stance significantly reduces the likelihood of violating data protection regulations, which often mandate that personal data be processed only for specified, explicit, and legitimate purposes and be adequate, relevant, and limited to what is necessary. Furthermore, it aligns with ethical considerations of respecting individual privacy. An incorrect approach that enables all detection features by default, including face detection and explicit content detection, without a clear business justification or consent mechanism, poses significant regulatory and ethical failures. This could lead to the unauthorized collection and processing of sensitive personal data, violating privacy laws that govern the handling of biometric information and personal attributes. Another incorrect approach that relies solely on post-processing filtering to remove sensitive information is also professionally unacceptable. This reactive measure is less effective and carries a higher risk of accidental data leakage. It fails to implement privacy by design, making the system inherently more vulnerable and potentially non-compliant with regulations that require data protection to be integrated into the design of systems and processes from the outset. Relying on such a method also increases the operational burden and the potential for human error in the filtering process. The professional decision-making process for similar situations should involve a thorough risk assessment of the data being processed and the intended use of the Cloud Vision API. This includes identifying potential sensitive data points that could be inferred or directly detected. Subsequently, a privacy-by-design approach should be adopted, configuring the API to enable only the essential features required for the specific business objective. Documentation of these decisions, including the rationale for feature selection and exclusion, is crucial for demonstrating due diligence and compliance. Regular review and auditing of the implementation are also vital to ensure ongoing adherence to privacy policies and regulatory requirements. Question 14. The efficiency study reveals that the current data pipeline for analyzing customer purchasing patterns is producing inconsistent results due to variations in how sales data is recorded across different regional databases. Specifically, dates are in multiple formats, currency values are sometimes represented with different symbols, and some product ID are missing or malformed. The goal is to create a unified, aggregated dataset that summarizes daily sales by product category and region, enriched with customer demographic information to identify high-value segments. Which of the following approaches best addresses these challenges to ensure accurate and actionable insights? Option A. Aggregate the sales data by region only, then clean the aggregated data and attempt to infer product categories and customer demographics from the clean sales figures. Option B. Implement a data pipeline that first cleans and standardizes all date formats, rectifies currency representations, validates and corrects product ID, then converts data types to appropriate formats, followed by aggregation of daily sales by category and region, and finally enriches the dataset with customer demographic information. Option C. Directly aggregate the raw sales data from all regional databases, converting all currency values to a single standard, and then joining with demographic data. Option D. Perform data enrichment with demographic data first, then aggregate the sales data, and finally clean the resulting dataset to standardized formats. The correct answer is C. Directly aggregate the raw sales data from all regional databases, converting all currency values to a single standard, and then joining with demographic data. Explanation. Scenario analysis. This scenario presents a common challenge in data engineering, ensuring data quality and consistency across disparate sources for a critical business function. The challenge lies in balancing the need for timely insights with the imperative to maintain data integrity and adhere to internal data governance policies, which are implicitly governed by the principles of data accuracy and reliability expected within a professional Google Cloud environment. Missteps can lead to flawed analysis, poor business decisions, and potential compliance issues if data is misrepresented or misused. Correct approach analysis. The correct approach involves a multi-stage data transformation process that systematically addresses data quality issues. 1. Data cleaning. Identifying and rectifying inconsistencies, missing values, and erroneous entries is paramount. This ensures that the data accurately reflects the real-world phenomena it represents. 2. Data type conversions. Standardizing data types, e.g., converting all date formats to ISO 8601 prevents downstream processing errors and ensures interoperability between different systems and tools. 3. Data formatting. Applying consistent formatting, e.g., standardizing currency symbols, address structures, enhances readability and facilitates accurate aggregation and analysis. 4. Data aggregation. Summarizing data at appropriate levels, e.g., daily sales by region, reduces complexity and provides higher-level insights, which is the stated goal of the efficiency study. 5. Data enrichment. Augmenting the dataset with relevant external information, e.g., demographic data for customer segments, adds context and depth to the analysis, leading to more actionable intelligence. This methodical approach, prioritizing data integrity at each step, aligns with best practices for data management and ensures that the final aggregated data is reliable, accurate, and fit for purpose, thereby supporting informed decision-making without compromising data trustworthiness. Incorrect approach is analysis. An approach that skips or inadequately addresses data cleaning and type conversion before aggregation would be professionally unacceptable. This would lead to the propagation of errors, skewed aggregations, and potentially nonsensical results. For example, if sales figures are aggregated with inconsistent currency formats or erroneous numerical entries, the total sales figures would be inaccurate, leading to flawed business conclusions. This failure to ensure data accuracy and consistency constitutes a significant professional lapse, as it undermines the very purpose of data analysis and can lead to detrimental business outcomes. Another incorrect approach would be to perform aggregation without considering data enrichment. While the aggregated data might be technically correct based on the raw inputs, it would lack the contextual depth necessary for a comprehensive efficiency study. This omission limits the analytical value and the ability to derive meaningful insights, representing a failure to maximize the utility of the data. A third incorrect approach might involve performing data type conversions without proper validation. For instance, blindly converting all numerical strings to integers without checking for non-numeric characters could lead to data loss or incorrect values, compromising the integrity of subsequent aggregation and enrichment steps. This demonstrates a lack of rigor in the transformation process. Professional reasoning. Professionals should adopt a phased approach to data transformation, starting with a thorough understanding of the data sources and the desired analytical outcomes. A robust data quality assessment should precede any transformation. Each transformation step, cleaning, conversion, formatting, aggregation, enrichment, should be designed to enhance data integrity and analytical value. Validation and testing should be performed at intermediate stages to catch errors early. The ultimate goal is to produce data that is not only accurate and consistent, but also provides actionable insights, adhering to the principles of responsible data stewardship. Question 15. Strategic planning requires a comprehensive approach to understanding customer feedback to drive service improvements. A data engineering team is tasked with analyzing a large volume of customer support interactions, including chat logs and email correspondence, to gauge overall sentiment, identify recurring issues, and categorize feedback themes. The primary objective is to derive actionable insights for product development and customer service enhancement without compromising customer privacy or violating data protection regulations. Which of the following approaches best aligns with these objectives and regulatory considerations? Option A. Implement sentiment analysis and entity recognition on unanonymized customer support transcripts, focusing on identifying specific customer complaints and the individuals associated with them, to enable direct follow-up and resolution by the customer service team, without implementing explicit data minimization techniques. Option B. Employ text classification to categorize feedback into broad categories, but bypass sentiment analysis and entity recognition to avoid any potential for inferring sensitive attributes from the text, thereby strictly adhering to a minimal data processing approach. Option C. Utilize Google Cloud Natural Language API for sentiment analysis to derive an overall sentiment score for each interaction. Form entity recognition to identify general product features and service aspects mentioned, and apply text classification to categorize feedback into predefined themes such as bug report, feature request, or usability issue. Ensure that personally identifiable information, PI, is masked or removed from the text prior to analysis, and that the aggregated insights are used for strategic decision-making rather than individual customer profiling. Option D. Process all raw customer support interactions through the Natural Language API, extracting all identified entities and their associated sentiment scores, and storing this detailed information, including any inadvertently captured PII, in a data lake for future ad hoc analysis and potential individual customer outreach. The correct answer is C. Utilize Google Cloud Natural Language API for sentiment analysis to derive an overall sentiment score for each interaction. Perform entity recognition to identify general product features and service aspects mentioned, and apply text classification to categorize feedback into predefined themes such as bug report, feature request, or usability issue. Ensure that personally identifiable information, PI, is masked or removed from the text prior to analysis, and that the aggregated insights are used for strategic decision-making rather than individual customer profiling. Explanation. This scenario presents a common challenge in data engineering, balancing the need for actionable insights with the responsible and compliant use of sensitive customer data. The core difficulty lies in extracting value from unstructured text while adhering to data privacy regulations and ethical considerations. The organization's goal is to understand customer sentiment and identify key topics to improve services, but this involves processing potentially personal information. The correct approach leverages Google Cloud Natural Language API's capabilities for sentiment analysis, entity recognition, and text classification in a manner that prioritizes data minimization and anonymization where possible. By focusing on aggregated sentiment scores, identifying general entities, like product names or service types, rather than personally identifiable information, and classifying feedback into broad categories, the organization can gain insights without directly exposing or unnecessarily processing sensitive customer details. This aligns with the principles of data privacy by design and by default, which are foundational to many regulatory frameworks governing data handling. The use of these tools for broad analysis, rather than granular individual profiling, minimizes the risk of privacy breaches and ensures compliance with regulations that mandate data protection and purpose limitation. An incorrect approach that involves extracting and storing personally identifiable information, PI, alongside sentiment scores or entity details would be a significant regulatory and ethical failure. This directly violates data privacy principles that require justification for collecting and retaining PII and often necessitates explicit consent. Storing PII in conjunction with sentiment analysis results creates a high risk of re-identification and misuse, potentially leading to violations of regulations like GDPR, if applicable to the exam's jurisdiction, which is U.S.-centric for this context, or similar U.S. data privacy laws. Another incorrect approach, such as performing sentiment analysis on raw, unanonymized customer support transcripts without a clear, defined business purpose, and without implementing robust access controls, also poses a substantial risk. This could lead to unauthorized access to sensitive customer conversations, violating confidentiality and trust, and potentially contravening regulations that protect consumer data and require secure data handling practices. A third incorrect approach, focusing solely on entity recognition without considering the context or potential for inferring sensitive attributes from those entities, could inadvertently lead to the collection of sensitive data categories, which often have stricter processing requirements. The professional decision-making process should involve a thorough risk assessment before implementing any data processing solution. This includes identifying potential privacy implications, understanding the specific data being processed, and mapping these to relevant regulatory requirements. The principle of least privilege should guide the design, ensuring that only necessary data is accessed and processed. Furthermore, a clear data governance policy should be in place, defining data retention periods, access controls, and procedures for handling sensitive information. When using cloud services like the Natural Language API, understanding the service's data handling policies and configuring it to align with organizational privacy standards is paramount. Question 16. During the evaluation of a customer churn prediction model trained on a dataset with a significant class imbalance, 95% non-churners, 5% churners, the data science team observes a high overall accuracy score. However, they are concerned that this metric might not adequately represent the model's ability to identify actual churners, which is the primary business objective. Which of the following evaluation strategies best addresses this concern and aligns with professional best practices for model assessment in such scenarios? Option A. Focusing on precision and recall for the churner class, alongside the F1 score and AUC, to understand the trade-offs between identifying actual churners and avoiding misclassifying non-churners. Option B. Prioritizing a single metric like precision for the churner class, assuming that minimizing false positives is the most critical aspect of churn prediction. Option C. Relying solely on the overall accuracy score, as it indicates the model's general correctness across all predictions. Option D. Evaluating the model exclusively on its ability to correctly predict the majority class, non-churners, as this represents the bulk of the dataset. The correct answer is A. Focusing on precision and recall for the churner class, alongside the F1 score and AUC, to understand the trade-offs between identifying actual churners and avoiding misclassifying non-churners. Explanation. This scenario presents a common challenge in machine learning projects, selecting the appropriate model evaluation strategy when dealing with imbalanced datasets and potential biases. The professional challenge lies in ensuring that the chosen metrics accurately reflect the model's performance in a real-world context, rather than just providing a misleadingly high overall accuracy. Careful judgment is required to avoid deploying a model that performs poorly on minority classes, which could have significant ethical and operational consequences. The correct approach involves using metrics that are robust to class imbalance and provide insights into the model's ability to correctly identify both positive and negative instances across all classes. Precision, recall, F1 score, and AUC are all valuable in this regard because they focus on specific aspects of classification performance beyond simple accuracy. For instance, recall is crucial when the cost of false negatives is high, while precision is important when the cost of false positives is high. By considering a suite of these metrics, a more comprehensive understanding of the model's strengths and weaknesses is achieved, leading to better decision-making regarding model deployment and further refinement. This aligns with professional best practices of thoroughness and a commitment to delivering reliable and fair AI systems. An incorrect approach would be to solely rely on accuracy, especially with imbalanced data. This is a significant regulatory and ethical failure because it can mask poor performance on minority classes. For example, a model that predicts the majority class 99% of the time might achieve 99% accuracy on a dataset where the minority class represents only 1% of the data. This would lead to a false sense of confidence in the model's effectiveness, potentially resulting in discriminatory outcomes or missed critical events if the minority class represents a sensitive or important category. Another incorrect approach is to focus on a single metric without considering the context of the problem. For instance, optimizing solely for precision might lead to a model that misses many true positives, low recall, which could be detrimental in applications like fraud detection or medical diagnosis. This demonstrates a lack of understanding of the trade-offs involved and the potential impact of model performance on stakeholders. A professional decision-making process for similar situations should involve 1. Understanding the business problem and the implications of different types of errors, false positives vs. false negatives for each class. 2. Identifying potential biases in the data and their impact on model performance. 3. Selecting a diverse set of evaluation metrics that address the specific challenges of the dataset e.g. imbalance and the problem domain. 4. Iteratively evaluating the model using these metrics and making informed decisions about model improvement or deployment based on a holistic view of performance. Question 17. Cost-benefit analysis shows that the current data storage and management practices on Google Cloud are incurring significant expenses. The organization needs to optimize these costs without compromising data integrity or the ability to meet potential regulatory audit requirements. Which of the following approaches best aligns with professional best practices for a Google Cloud professional data engineer in this scenario? Option A. Implement a tiered storage strategy by analyzing data access patterns and moving less frequently accessed data to colder storage classes, while optimizing data processing pipelines to reduce redundant storage and computation. Option B. Migrate all data to the lowest cost storage tier available on Google Cloud, regardless of access frequency or performance implications, to achieve maximum immediate cost reduction. Option C. Aggressively delete historical data that is not actively being accessed, assuming it is no longer needed for business operations, to immediately reduce storage volume. Option D. Adopt a third-party data compression and deduplication solution that promises significant storage savings, without conducting a thorough security and compliance review of the tool. The correct answer is A. Implement a tiered storage strategy by analyzing data access patterns and moving less frequently accessed data to colder storage classes, while optimizing data processing pipelines to reduce redundant storage and computation. Explanation. This scenario is professionally challenging because it requires balancing cost-effectiveness with data integrity and compliance requirements, which are paramount in regulated industries. The core of the challenge lies in optimizing data storage and management processes to reduce operational expenses without compromising the ability to meet regulatory obligations or the quality of insights derived from the data. Careful judgment is needed to select solutions that offer tangible cost savings while adhering to established data governance principles and potential future auditability needs. The correct approach represents best professional practice because it prioritizes a phased, data-centric strategy that leverages Google Cloud's native capabilities for cost optimization. By analyzing data access patterns and implementing tiered storage solutions, e.g., moving less frequently accessed data to colder storage classes like archive or cold line. The organization can significantly reduce storage costs. Furthermore, optimizing data processing pipelines to reduce redundant computations and temporary storage usage directly impacts operational expenditure. This approach aligns with the principle of responsible data stewardship, ensuring that cost savings do not come at the expense of data availability for compliance or business needs. It also demonstrates a proactive understanding of cloud cost management best practices, which is a key competency for a professional data engineer. An incorrect approach that focuses solely on aggressive data deletion without a clear retention policy or audit trail is professionally unacceptable. This could lead to regulatory violations if data required for compliance or legal discovery is permanently removed. Such an action would represent a failure in data governance and could expose the organization to significant legal and financial penalties. Another incorrect approach that involves migrating all data to the cheapest storage tier without considering access frequency or performance requirements would be detrimental. While it might offer immediate cost savings, it would likely lead to unacceptable performance degradation for critical applications and users, hindering business operations and potentially impacting data usability for analytics. This demonstrates a lack of understanding of the trade-offs involved in storage tiering and a failure to align technical solutions with business requirements. Finally, an approach that relies on external, unvetted third-party tools for data compression or deduplication without thorough security and compliance reviews is risky. This could introduce vulnerabilities, compromise data privacy, or violate data residency requirements, leading to regulatory noncompliance and potential data breaches. The professional reasoning process for similar situations should involve a systematic evaluation of data lifecycle management. This includes understanding data classification, access patterns, retention requirements, driven by business needs and regulations, and performance SLAs. A thorough cost-benefit analysis should then be performed for various optimization strategies, considering not just direct storage costs, but also processing, egress, and potential compliance risks. Prioritizing solutions that offer a clear return on investment while maintaining data integrity and compliance is key. Collaboration with legal, compliance, and business stakeholders is crucial to ensure all requirements are met. Question 18. The control framework reveals that the data engineering team is tasked with integrating data from various sources, including a production MySQL database containing customer PII, a MongoDB cluster storing user activity logs, a Kafka topic for real-time event streams, and a set of external APIs providing product information. The team must ensure that all data is ingested securely, processed efficiently, and remains compliant with data privacy regulations. Which approach best addresses these requirements? Option A. Store all data in a publicly accessible object storage, relying on application-level security to protect sensitive information. Option B. Utilize Cloud SQL for the MySQL data with robust encryption and access controls. Leverage Dataproc for processing MongoDB data with appropriate security configurations. Ingest Kafka streams into pub/sub with encryption and dead letter queues. And use cloud functions to securely fetch data from APIs with authentication and rate limiting. Option C. Stream all data directly into BigQuery without any intermediate processing or security checks to maximize query performance. Option D. Ingest data from all sources into a single, unencrypted cloud storage bucket, applying basic IAM roles for access control. Correct answer is D. Ingest data from all sources into a single, unencrypted cloud storage bucket, applying basic IAM roles for access control. Explanation. This scenario presents a common challenge in data engineering, integrating diverse data sources while adhering to strict data governance and compliance requirements. The professional challenge lies in selecting the most appropriate ingestion and processing strategy that balances performance, cost, and regulatory adherence, especially when dealing with sensitive customer data. Careful judgment is required to avoid data breaches, ensure data integrity, and meet auditability standards. The correct approach prioritizes a secure, auditable, and scalable method for ingesting and processing sensitive customer data from multiple sources. This involves understanding the nature of each data source and applying appropriate controls. Relational databases, using a managed service like Cloud SQL with appropriate access controls and encryption is crucial. For NoSQL databases, similar security measures and potentially schema validation are important. Streaming data from Kafka or pub/sub requires robust error handling, dead letter queues, and encryption in transit and at rest. File-based data, especially sensitive information in CSV or JSON, necessitates encryption at rest and strict access policies. APIs require authentication, authorization, and rate limiting. Ultimately, the chosen solution must facilitate data lineage tracking and compliance with data privacy regulations. An incorrect approach would be to indiscriminately dump all data into a single, less secure storage solution without proper encryption or access controls. This poses significant regulatory and ethical failures. For instance, storing sensitive customer data from a relational database in an unencrypted object storage bucket without granular access controls violates data privacy regulations, e.g., GDPR, CCPA, depending on the exam's specified jurisdiction, by failing to protect personal identifiable information, PI. Similarly, ingesting streaming data without implementing mechanisms to handle malformed records or potential data corruption can lead to inaccurate reporting and compliance issues. Using unauthenticated or poorly secured APIs for data ingestion bypasses critical security checks, exposing the system to unauthorized access and data exfiltration, which is a direct violation of security best practices and potentially data protection laws. The professional decision-making process should involve a thorough assessment of data sensitivity, regulatory requirements, performance needs, and cost implications for each data source. A risk-based approach is essential, where higher sensitivity data receives more stringent security and governance controls. Data engineers should consult with legal and compliance teams to ensure all chosen solutions meet regulatory mandates. Prioritizing solutions that offer built-in security features, audit trails, and data lineage capabilities will lead to a more robust and compliant data architecture. Question 19. Regulatory review indicates that a financial services firm is developing a predictive model using Vertex AI to assess loan application risk. The firm must ensure the model is not only accurate, but also demonstrably fair, transparent, and compliant with data privacy regulations. Which Vertex AI strategy best addresses these multifaceted requirements throughout the model lifecycle? Option A. Utilize Vertex AI Auto ML for initial feature engineering and model prototyping, followed by deployment with comprehensive Vertex AI model monitoring for drift, bias, and performance metrics, and integrate explainability features. Option B. Develop a custom model using advanced algorithms, deploy it with minimal monitoring, and rely on post-hoc analysis for any fairness concerns. Option C. Focus solely on hyperparameter tuning for maximum predictive accuracy using a black box model, and deploy it without any specific monitoring for fairness or drift. Option D. Train a model using sensitive customer data without explicit consent for AI training, and deploy it with basic performance metrics only. The correct answer is B. Develop a custom model using advanced algorithms, deploy it with minimal monitoring, and rely on post-hoc analysis for any fairness concerns. Explanation. Scenario analysis. This scenario presents a common challenge in regulated industries where data privacy and model explainability are paramount. The core difficulty lies in balancing the need for sophisticated model performance with the strict requirements for transparency and auditability mandated by data protection regulations. Organizations must demonstrate that their AI systems do not perpetuate bias, that their decision-making processes are understandable, and that sensitive data is handled appropriately throughout the model lifecycle. The professional challenge is to select a Vertex AI strategy that meets these dual demands without compromising either accuracy or compliance. Correct approach analysis. The correct approach leverages Vertex AI's integrated capabilities for responsible AI development and deployment. Utilizing Auto ML for initial model exploration and feature engineering allows for rapid iteration while adhering to predefined constraints. Crucially, employing Vertex AI model monitoring for drift detection and bias assessment post-deployment is essential for ongoing compliance. This proactive monitoring ensures that the model's behavior remains within acceptable ethical and regulatory boundaries, providing an auditable trail of its performance and any deviations. This aligns with the principles of data minimization, purpose limitation, and accountability, often found in data protection frameworks, ensuring that the model's impact is understood and controlled. Incorrect approach is analysis. Deploying a model trained with custom code without robust monitoring for bias or drift fails to meet regulatory requirements for ongoing oversight and accountability. This approach risks introducing or perpetuating discriminatory outcomes that could violate anti-discrimination laws and data protection principles. Relying solely on hyperparameter tuning without considering feature engineering for bias mitigation overlooks a critical step in responsible AI development, potentially leading to models that are technically optimized but ethically flawed. Furthermore, deploying a model without any form of explainability or bias assessment, even if it achieves high accuracy, is a direct contravention of regulations that demand transparency in automated decision-making processes, particularly when they affect individuals. This lack of transparency can lead to significant legal and reputational damage. Professional reasoning. Professionals must adopt a risk-based approach, prioritizing compliance and ethical considerations from the outset of any AI project. This involves understanding the specific regulatory landscape applicable to the data and the intended use of the model. The decision-making process should involve 1. Identifying potential regulatory pitfalls, e.g., bias, privacy, explainability. 2. Selecting tools and services within Vertex AI that offer built-in safeguards and monitoring capabilities. 3. Designing a workflow that incorporates continuous evaluation and auditing. And 4. Ensuring that documentation clearly outlines the model's development, deployment, and monitoring processes for audit purposes. Question 20. The performance metrics show a significant drop in accuracy when the model is deployed to production compared to the validation set results. The data preparation pipeline involved calculating imputation values and scaling parameters using the entire dataset asterisk before asterisk splitting it into training, validation, and test sets. Which of the following data preparation strategies, when applied correctly, would best mitigate this issue and ensure reliable model evaluation? Option A. Perform feature engineering and data preprocessing steps, including calculating imputation values and scaling parameters, independently on each of the training, validation, and test datasets asterisk after asterisk the initial data split. Option B. Calculate imputation values and scaling parameters using the entire dataset and then split the preprocessed data into training, validation, and test sets. Option C. Train the model on the entire dataset and then use a separate, smaller dataset for validation and testing. Option D. Apply feature engineering and data preprocessing steps to the entire dataset and then perform a random split into training, validation, and test sets. The correct answer is A. Perform feature engineering and data preprocessing steps, including calculating imputation values and scaling parameters, independently on each of the training, validation, and test datasets asterisk after asterisk the initial data split. Explanation. This scenario is professionally challenging because the observed performance degradation, despite seemingly standard data preparation steps, indicates a subtle but critical flaw in the feature engineering or data splitting strategy. The pressure to deliver a performant model quickly can lead to overlooking fundamental principles. Careful judgment is required to diagnose the root cause without resorting to superficial fixes. The correct approach represents best professional practice because it directly addresses the potential for data leakage during the feature engineering process. By performing feature engineering asterisk after asterisk splitting the data, each dataset train, validation, test is treated independently. This ensures that the model learns patterns solely from the training data and is evaluated on unseen data, preventing an inflated sense of performance. This aligns with the principle of robust model evaluation, which is crucial for reliable deployment and avoiding misrepresentation of model capabilities, a key ethical consideration in data science. An incorrect approach that involves calculating aggregate statistics, like mean or standard deviation, for imputation or scaling asterisk before asterisk splitting the data is a significant regulatory and ethical failure. This constitutes data leakage, where information from the validation or test sets inadvertently influences the training process. This leads to an overestimation of model performance, potentially resulting in the deployment of a model that fails in production. This misrepresentation of model efficacy can have serious consequences, especially in regulated industries, leading to non-compliance with data governance and responsible AI principles. Another incorrect approach, such as applying transformations learned only from the training set to the validation and test sets, but doing so before the split is also problematic. While the intent might be to apply consistent transformations, the act of learning these transformations from the entire dataset before splitting introduces leakage. The validation and test sets then contain information about the training set's distribution, compromising the integrity of the evaluation. This violates the core tenet of independent evaluation and can lead to regulatory scrutiny for flawed model validation processes. The professional reasoning process for such situations should involve a systematic review of the data preparation pipeline. Start by questioning the order of operations, feature engineering, scaling, imputation, and data splitting. Always prioritize splitting the data first to establish distinct sets for training, validation, and testing. Then, apply any data transformations or feature engineering steps independently to each set, learning parameters like means, standard deviations, or feature importance only from the training data and applying them to all sets. This iterative, principled approach ensures data integrity and reliable model evaluation, preventing ethical breaches and regulatory noncompliance.